What if I told you sometimes keeping a wrong data, or you may say using an outlier, improves your estimate? You are surprised, as it sounds strange, isn't it? But statistics is full of surprises. Imagine this situation. You collect n observations x1, x2, xn from a population. But here is a twist. Suppose out of these observations, one is an outlier. It seems a spurious observation. Without any loss of generality, let us assume that this observation is xn. You may call it as a contaminated observation also. This observation doesn't fit with the other n minus 1 observations, x1, x2, xn minus 1. It seems to come from some other population. Let the observations x1, x2, xn minus 1 come from a population with mean mu and variance sigma square. And the suspected observation xn come from a population with mean nu and the same variance sigma square. Now comes the dilemma. Should we omit this suspicious observation xn, or should we include this anyway? Most of the people and even many analysts would say, remove this observation. Remove the outlier. It will distort the result. Yes, it seems reasonable. But let us look deeper. We calculate mean x bar of the first n minus 1 observations. That is, we calculate mean excluding the outlier. So, x bar is equal to 1 by n minus 1 summation I from 1 to n minus 1 xi. Now, ignoring the fact that there is an outlier, let us compute the mean using all the n observations, that is, including the outlier. Let this mean be denoted by mu curly. So mu curly is given by 1 by n summation I from 1 to n xi. And obviously this is equal to n minus 1 x bar plus xn whole divided by n. Now let nu minus mu be equal to delta sigma. That is the difference between the two population means, be equal to delta sigma, where sigma is the common population standard deviation. The mean squared error of mu curly would be given by expected value of mu curly minus mu whole square. Now, substituting the expression for mu curly, this is equal to expectation of n minus 1 x bar plus xn whole divided by n minus mu whole square. And adjusting some terms here and there, it can be written as 1 by n square expectation of n minus 1 into x bar minus mu plus xn minus nu plus nu minus mu whole square. Now remember here, nu minus mu is equal to delta sigma. So substituting nu minus mu equal to delta sigma, it comes out to be sigma square by n plus sigma square delta square by n square. And this is less than sigma square by n minus 1, which is the variance of x bar. If delta square is less than n by n minus 1, which is always true if delta is less than or equal to 1. Here is the surprising result. If the difference between the two population means is not too large, say within 1 standard deviation, then including even a spurious observation can actually reduce the mean squared error. Even if an observation comes from a different population, even if it is technically wrong, it can still improve your estimate as long as it is within 1 standard deviation. Why does this happen? Because including more data, even slightly imperfect data, can reduce variance. And in small samples, variance reduction can outweigh the bias introduced by that outlier. So, the trade-off is the decision to omit or include an outlier is not always obvious. Blindly removing data can actually make your estimate worse. So next time, when you see an outlier, do not rush to delete it. Ask yourself, is it truly harmful? Or could it be actually helpful? That is the beauty of statistics. Statistics is full of surprises. Thank you. Thank you very much.